right. Well, thanks for coming to our session. I'm happy to introduce Tom Tegtmeyer, who's going to be talking to us about re-examining the Oracle's league bias in the age of the universal designated hitter. So, go ahead, Tom.
Thank you. So this is the third in what I hope to be a trilogy of talks about Oracle and ranking baseball players, just batters and hitters, batters and pitchers. Let me first talk about the Oracle. It's a graph-based or network-based method. You can use a directed graph to display the results of a tournament or league season. An edge going from one to another indicates that, or it goes towards a winner of the match. You can imagine independent voters moving along the graph, randomly choosing a new edge at each vertex. If the distribution of voters among the vertices has a steady state, we can use that distribution to rank players or teams. Note that you have to do a little bit of adjustments because, for instance, team B didn't lose, and so voters can't leave B if they get there. So various ranking methods have various ways of dealing with these situations. What the Oracle does is it introduces a new player or team that beats and loses to every team. This was developed by me and a couple of my colleagues at Trinity back in 2014. So the nice thing about the Oracle is you can, depending on what you want to do, you can choose how to weight the edges up to and away from the Oracle. For instance, edges down from the Oracle might have weights that are proportional to the number of wins a team has. Weights of the edges leading up to the Oracle can be manipulated to change the amount of traffic that flows through the Oracle. And you can also include point difference and stuff like that if you want to favor points and those sorts of things. So once the Oracle is included, you've got this graph. There's an adjacency matrix with the weighted edges. You can turn it into a stochastic matrix. And then the Frobenius theorem guarantees that the stochastic matrix is going to have a stationary vector, and the vector gives us our Oracle rankings. We'll throw the Oracle out, so not to include that individual in the ratings, but anyway. Our original paper used regular season NFL games, and we got some pretty good results tweaking the edges up to and from the Oracle. Also, after I had, or while I was in exile in Missouri, my colleagues started playing around with around playoff time in the NBA. Used it to predict the results of the playoffs, and remarkably predicted the Spurs to win the NBA championship. Got a little local coverage for that, and they actually did win the championship that year. Other applications, lizard battles ranking. We have a colleague at Trinity who works with anole lizards, and if you're curious about lizard battles, I can tell you about them at the end of the talk. So I was in exile in Missouri and was learning R at the time, going through, can't see the analyzing baseball data with R. That's the best way to learn R, in my opinion. I was wondering if I could, fiddle around with the Oracle method in baseball, but not for teams, but for individual hitters and batters, because each plate appearance is basically a mini competition between hitters and batters. So I'm going to count hits, walks, and hit by pitches as wins for the batter, and then everything else except sacrifices a win for the pitcher. Then we can use those results to rank pitchers and batters simultaneously. So again, we're only considering who was pitching, who was batting, and what the result was. No additional information to create our rankings. Some possible challenges. NFL regular season, 272 games. In 2022 in Major League Baseball, or at least according to what I could get from the retro sheet play-by-play files, there were 180,000 plus pitcher batter battles. So it's a much bigger system, a lot more individuals involved, and a lot more results to deal with. There's a disparity in the number of battles per player. You know, in NFL, everyone plays the same number of games, but if you consider individual hitters and pitchers, some people only had one plate appearance, or only faced one batter, and some people had as many as 879 of those. So, and also pitchers usually win. More around 2/3 of the time or more, pitcher wins. So I need to choose the weights. We'll give each pitcher batter edge weight 1. And then for the Oracle 2-player edge weights, basically going to base it on their for the batters on their on base percentage. Have to adjust it a little bit. You need to add 1 to make sure that people who didn't get any hits or walks or whatever still are connected, and to make sure that those people don't have a weight of 1, you'll add 2 to the denominator. So again, H star in this is hits plus walks plus hit by pitches. And that for pitchers, the weight is going to be, you know, the number of batters faced minus those things. Again, +1, and then divided by number of batters faced +2. Again, these are adjusted because I'm not counting sacrifices. So if you're looking up some of these results, they're going to be a little off from the season totals that you see under batters faced or plate appearances. Okay, so here's some results. So starting with 2018, you see some familiar names here. What I like to see is it's not purely a ranking of how many, these are pitchers, how many, what their opponent's on base percentage was. And it's not purely how many batters they faced. There's a little variability in that. So I mentioned this is a trilogy. The first time I gave a talk, I neglected to look at my data very carefully before the talk, and didn't notice that, well, my first talk was using 2017 data, but the 2018 data has the same problem. All these are National League players. And it's not hard to figure out why this is the case. In the National League at the time, pitchers had to bat, and so that was not totally a win for the pitcher every time, but a good bet that the pitcher would get a win against pitchers as a batter. By the way, pitchers as pitchers and pitchers as batters are treated as separate individuals in these ratings. So yeah, so my next talk was about how to fix that, but we don't have to worry about that anymore because of the universal DH. So I'm going to show some of the results for subsequent years as well. But first, just a little bit more on the 2018 ratings. The highest ranked American League pitcher came in at 20, Corey Kluber. If you look at back-to-back histograms for the ratings, you see that there really aren't any AL batters that got a rating above 0.8. By the way, take the original ratings and then rescale them so that the highest individual has a rating of 1. And again, after adjusting that, there weren't any pitchers with a rating of above 0.8. And if you look at some of these summary statistics, again, a higher mean rating for NL pitchers compared to AL pitchers, median again higher. The lower percentiles aren't particularly interesting because there are a lot of people who don't do much in those lower ratings. But higher 75th percentile for NL and definitely higher 90th percentile for the National League pitchers. And this persists. This is 2019. All of the top 20 pitchers. Again, I show the top 8 because that's about as many as I can fit on a slide. Interesting. Merrill Kelly led the league in losses that year, but he faced a lot of batters, so that worked in his favor. I mentioned again, they get rescaled so that the highest pitcher has a rating of 1. The gap is going to vary from year to year. This gap is a lot larger than the gap previous year. 2020 was shortened, and both leagues had designated hitters. And the bias pretty much went away. We'll see summary stats a little bit later. But 8 of the top 20 pitchers in 2020 came from the AL, including the top pitcher. And again, you see a lot of familiar names on the list. (2021) back to pitchers batting in the National League. And once again, all of the top 20 pitchers were from the National League. Again, many familiar names in the rankings here. So yeah, 2021 was the final year with pitchers batting before the universal DH. So here are those years leading up to 2022. Again, 2018, 19 of the 20 pitchers in the top 20 were from the NL. All of them in 2019, the adjusted year with the DH in the NL. More even split, and the AL pitchers were had a higher 90th percentile, a higher mean and median. Then back to normal in 2021. And again, remember, these numbers are going to vary from year to year. For reasons I can't totally explain, other than noting that there is a gap often between the top pitcher and others. Okay, 2022. Here are the rankings. 7 of the top 20 are from the AL. Only 2 of the top 8 from the AL. But we'll again look at the summary statistics and just at that. Miles Mikolas was 12-13 this year, or in 2022, but he led the ratings. He was also on the list in 2018, if I'm not mistaken, with very similar statistics, although his win-loss record was a lot better that year. So it's nice to know that this method is, picking out that they're doing well in some regard, at least, even if it doesn't show up in the ERA or in the win-loss percentage. NL pitchers a little bit higher at the top, but then like evens out pretty much, at least in the higher percentiles. And yeah, summary statistics, AL, NL, pretty close to each other. Top 20 is a little bit dominated by the NL, but when you get to the top 50, which are still among the elite pitchers, 24 of those are from the AL and 26 from the NL. So at least with the 2 years that I have data for, where there is a universal DH, there seems to be a lack of or no league bias, whereas in years with a DH, there seemed to be a definite bias in these ratings towards the NL. So 2023 retro sheets play-by-play data doesn't come out until later on, so I didn't have access to those. That's what I used to create most of the other ones. I have played around with StatCast a little bit, and I did get those numbers, but the plate appearances / batters faced numbers didn't match or weren't close. So I'm trying to figure out what's missing from those totals. But if anyone's curious, I will, once I get the retro sheet values, or if I can figure out StatCast, I will let you know. Limitations. There is a bias towards players with more batters faced or plate appearances. That's going to affect relief pitchers in particular. You're not going to see many relief pitchers in the higher rankings, in the higher ranks. I haven't dealt with pitchers that change leagues over the course of the season. That's obviously something that happens. Up and down weights are somewhat arbitrary, and I'm not sure if there's a good way to compare the two different methods, say which one is better than another. You know, with NFL, you can use the rankings for future predictions, but again, pitchers usually win, so it's hard to easy oracle to predict who's going to win in a pitcher batter battle. Here's where I get my data from. If you're curious about the Oracle in general, we have a website. Hasn't been updated this year, but that's my talk. Thank you.
Excuse me. Thank you, Tom. If we can express some virtual gratitude for him, and maybe we have time for one quick question if there's one out there.
I do have batting. Anyone? This is from 2018.
There was a question about in chat.
Yes, they were. Pitchers as pitchers and pitchers as batters are considered different individuals. Well, one thing I tried to do to adjust for this bias was actually throw out pitchers as batters to see how that affected the rankings, and that evened out the bias as well.
Well, great. Well, thank you very much. Very, very interesting. So, Jay, did you want to see if we can get your screen shared then, and we can get started?
Yeah, I'll start right now. All right, I hope everyone has seen my screen.
Yep.
Good morning, everyone.
I can introduce you real quick. We have Jay Lee here from Jericho High School, and he's going to talk about using logistic regression to recalibrate some regional miscalibration of ELO ratings. So take it away.
Thank you. So hi, everyone. My name is Jay. I'm from Jericho High School. I did this project this summer with Dr. Charlie from Davidson College. And the focus of this project is on ELO ratings. So I'll start with some background on this rating system. So the ELO rating system is a general rating system devised for playing in chess. So that's where I was inspired from, but it's widely used in other sports and also non-sports. So areas such as education and healthcare, you can also see its usage. One of the important characteristic of it is that it is an iterative algorithm. So it updates its rating after each game rather than, unlike, say, Massey or Colley's methods, where it accounts for all the results once and doesn't update after each game. It also uses expected score calculated with a logistic regression. So these will be recurring topics I'll be using in my method as well. The main focus for this project is on the problem of isolated rating pools in ELO rating system. So I will be using a lot of examples as chess players, but please be aware that this could apply to basically any field that ELO rating is involved in. So most ELO fields have some kind of geographic constraints, and a lot of times because of these constraints, players are often grouped in their local areas, and this is a problem because when there are not enough games between people from different areas, then there's a lack of information that will cause a miscalibration. So this happens in chess, but also in other sports. So college football and soccer are two I can think of right now, but I'm sure every sport will have some kind of geographic deviation. So for ELO ratings system, part of this is that because it is iterative, it is meant to be easy to calculate, but it takes quite a few games to reach an equilibrium state to have an accurate ratings. This method hopes, so this for this project, I devised a method that hopefully will, well, not hopefully, but the method I devised has the intention to not use the iterative nature of ELO to account for the ratings between different regions differently. So I made a few assumptions in my project to simplify the process a little bit. So first, there are two isolated rating pools. So here we will not account for the cases where the players are divided into many different regions and all interacting with each other. I also assume the player's strength to be constant within the time frame. I also assume that relatively speaking, the ratings inside the region is accurate enough, and that there's already a classification such as geographic that divide the players into categories. So these are all assumptions that could introduce further work without these assumptions, but they provide a good ideal model for my project to continue on. Onto my method. So in the ideal case, a good way to approach two isolated rating pools is to make use of the fact that because inter-regional games are rare, we want to account for it at the same time, similar to Colley or Massey. So each game is a piece of information that could provide some estimate on the ratings. However, this only happens nicely when every game is a draw, because then we can say the rating of player from group A is roughly equal to the rating of player from group B. But when a game is not a draw, but a win or a loss, then there's no easy way to directly estimate the ratings of two players. So instead, in this project, I use logistic regression to estimate the expected scores between players. Sorry. And from the expected scores, I estimated the ratings from it. So I'll go into more details about step 2 and 3 in the next slide. But I want to point out that there is an edge case which this project does not account for, which is when the results are overwhelmingly lopsided toward one side or the other. So if every player from Group A always win games from over players from Group B, then there's not enough information to set an upper bound on the playing strength of Group A. And ELO rating system would just suggest that one group has a positive infinity, the other group has a negative infinity. So that's not very helpful. I have purposely ignored that case in this project, but it is still a point to point out, nonetheless. So I also made use of the fact that in the ELO rating system, part of the design is that Arpad Elo, the inventor of the system, designed so that the draw is half a win and half a loss. So here I made use of this fact and converted each score as some kind of true score, where a win is two small wins, a draw is a win and a loss loss is two losses. So this avoids the problem of ties and will make logistic regression easier to calculate. Using this, I could convert each interregional game to 2 data points with a 2-dimensional input, the rating of player A and rating of player B. So logistic regression gives an expected, using these data points, logistic regression could calculate every single expected score using the input of a player from with rating RA and a player with rating RB from Group A and Group B respectively. Then I use the fact that because two players with the same playing strength must have an expected score of 1/2 when playing against each other, that means beta 0 plus RA beta 1 plus RB beta 2 must equal to 0. And this will be a linear relationship that help convert ratings of one group to the ratings of the other. So this will successfully address the problem of miscalibration when R and RB are not adequately adjusted against each other. All right, so because I use a more or less ideal model where it's quite difficult to replicate in real life, I decided to use the simulated trials using simulated players and simulated games where the expected score is the ELO estimate using the logistic regression. However, I have every player from Group A systematically underrated by some initial rating difference D, while every single player from Group B is systematically overrated by B points. Yeah. So this will give us an initial miscalibration, and this program will fix this miscalibration as more and more interregional games are played. So in this graph, the N on the bottom, on the x-axis, is the number of interregional games. As more games are played, naturally, the miscalibration decreases and the room mean square error will approach not necessarily 0, but some lower value. I have included D equal to 0 as a control group where there is no miscalibration to begin with. This kind of provides an upper bound of how good this method can be, because there will be some variation that comes with a probabilistic approach. Another variable which I tested on is the number of players of the regions. So in the graph here, I assume that each region will have 100 players, but I also did simulation on other region sizes. So for 100 players for 1,000 players in Group A and 100 players in Group B, and 100 players in Group A and 1,000 players in Group B. As you can see, the results are slightly different. The reason for this is because I adjusted every rating of Group A to Group B before calculating the root mean square error. So this will cause a slight bias to, when for a better result when Group B has more people. So this is a slight, I guess, underestimate of this problem's efficacy of correcting the miscalibration, but it still demonstrates the results quite well. So lastly, I want to point out a few further ideas that could be worked upon. So the assumptions I made in this project, such as 2 isolated rating pools and constant plane strength, could both and accurate interregional ratings and already classified isolated region pools, they could all be improved upon without these as projects without these assumptions. So, for example, there could be multiple rating pools, and one could test how that system will evolve if, say, this method is applied twice. There could also be a time-dependent plane strength, where a player's strength changes with time a little bit. In the case of inaccurate interregional ratings, this method should still work for relatively small error by the ELO ratings, but when the ELO rating has big problem on its own, then this method will generally fail to correct it. Lastly, the classifying isolated region pools is another important part which this project neglects. So this project starts with the assumption that we can already determine regions, so different regions of the players, but unless it's very specifically divided, such as between different leagues, different I know different parts of the football competition. Generally, if it's between these parts, then there's already a well-defined regions. But in the more general sense, if someone wants to classify different geographic regions, it might be more helpful if there's a statistical way to approach it rather than subjectively defining the regions. And lastly, I want to talk about what the application of this method is. Even though I did more or less theoretical work, because this project is directly related to the ELO rating system, it could basically be applied everywhere where both ELO and geography is, or just isolated regions are involved. So sports such as football and soccer all have similarities with the examples shown here. Yeah, that's about it. If anyone has any question, I'll be willing to answer.
So thank you very much, Jay. Yeah, are there any questions for him? So you mentioned applying this to maybe sports like football. Is there going to be a challenge involved with not having as many games? College football, maybe teams play 13, 14 games. Is that going to be a challenge for this particular method?
I think So I'm not familiar enough about the specific of college football, but I know that there are geographic challenges. So I guess yeah. So this method assumes that inside regions the ratings are accurate on its own, and then use that as a basis to correct between regions. So it will be a good example of the regional divide. Um, so the college football will be a good example of this kind of regional divide, and it'll be a good example to apply it upon. But I'm not sure if the intra-regional part would be good enough as a basis.
Thank you. Any other questions for Jay? But thanks again, Jay. We appreciate your talk.
Thank you all for listening.
And Chris or Ryan, whoever's going to be sharing your screen, if you want to get that set up, we've got a couple minutes until our next talks, but we can start getting prepared.
Start getting that ready.
Yeah, we can go ahead and yeah, if you've got a title screen or something to share, make sure the sharing works. Go ahead with that.
Yep.
Looks good. As Russ just shared, I think we got about 3 minutes and then we can get started.
Sounds good.
All right, well, so it's 11:40, so let's welcome Chris Greve here from Neumann University, who's going to be speaking to us about the UFC scoring model. Go for it.
All right. Well, thank you everyone for joining. So I decided to make a UFC scoring model because UFC scoring can be very biased. So we'll get into that. So basically what the UFC is it's the Ultimate Fighting Championship. The UFC was founded in 1990. And in the UFC, there are a few ways you can win a fight. First off, there's a knockout or a TKO, which is basically when someone beats someone and they have to stop the fight. There's also a submission, which is a wrestling move where they end the fight because of that. There's referee stoppage if it's getting out of hand. There's also disqualifications if the fighters are not playing fairly. And then what I wanted to focus on today is the judge's decision. So that is, if there's no knockouts, if the fight isn't stopped, it goes the full distance. It comes down to the judges to decide who wins the fight. And in the UFC, often the judge's decision is very controversial. The judges score each round. So it's not on the total fight. They don't look at the total fight stats. They say, okay, fighter one won the first 2 rounds and fighter 2 won the next 3 rounds. So we think that fighter 2 wins, which it really doesn't do a good job at telling the whole story. And there's no real guidelines on how to pick the winner for each round. It kind of just goes off their eye test, who they think looked better. Sometimes they might look at stats, but a lot of times they don't even get that information until well after the fight. And a lot of the time, boxing judges are used for the UFC, and they don't really know anything about the UFC rules, kind of how to weight the different types of moves they do. And they just kind of pick a winner based on who they think looked the best. So our goal is to create a model that gives the fight, that given the fight data, can fairly choose a winner. So some of the model components that we included in this was we used the 1993 to 2021 UFC dataset. It has all fights that occurred from that time period, and we filtered it to only include fights that came down to a judge's decision. So with this, we made a logistic regression model, and the dependent variable for this was the binary variable. Did fighter B win? If they won, it's a 1. If they lost, it's a 0. So 1 equals yes, 0 equals no. And the independent variables that we tested were the difference between fighter B and our stats. So that included their total strikes, body strikes, clinches, control time in seconds, ground strikes, head strikes, knockdowns, leg strikes, reversals, significant strikes, and takedowns. In order to pick the best model, I used the stepwise selection feature to add and remove independent variables to find the optimal combination of variables that explained the winner of the fight. So overall, I decided that the 7 independent variables to be included were the difference in control time, difference in ground strikes, difference in head strikes, difference in knockdowns, difference in reversals, difference in significant strikes, and difference in takedowns. Some stuff that wasn't included in the model included the difference in total strikes, because that was kind of already explained in all the other strikes that I just mentioned before. So that there's a lot of multi-collinearity there, and that wasn't really necessary to put in. Also, it didn't find leg strikes to be all that important, or clinches, or body strikes. And body strikes and leg strikes could also a lot of the time be explained in the significant strikes. So they didn't really have a lot of standalone value there. So I'm going to pass it over to Ryan now to explain some of the results we got.
Okay, hello everybody. So yeah, so as Chris was saying, we ran this logistic regression. We did it stepwise since we had a whole bunch of variables to deal with. And this is the model that we came up with using the 7 independent variables that Chris discussed. They're all continuous. Obviously, the dependent variable is not continuous, but all these independent variables are. And as you'll see by taking a look at the p-values on the far right, they are all highly statistically significant, except for the difference in ground there. Still statistically significant, but that one was a little more borderline. Everything else came out to be, though, highly statistically significant. And on the far left here, we've got our parameter estimates for each of these. Now, keep in mind that since we're dealing with a logistic regression, these parameter estimates aren't super straightforward to interpret. It's not like a 1 second increase in control, increase is related to an increase in something else by 0.4028. But rather, we're dealing with having to exponentiate these parameter estimates in order to figure out how many times more likely someone is to win a match due to an increase in one of these differences. We'll talk about that a little bit later, but again, one of the, I don't know if I want to call it a drawback, but just one of the things to know about logistic regression is at face value, the parameter estimates aren't, super interesting. We have to play around with them a little. So I guess if you go to the next slide, please, Chris. So over here, we have some summary statistics for the model. The R squared, which is kind of an adjusted type of R squared, because we're dealing with logistic regression, sort of similar to a Nagelkerk R squared, is 0.3775. That might not sound that fantastic at first, because as we all know, R squared values range from 0 to 1, with 1 being perfect. But when we go down to this bottom table here, we see that our model does a very nice job of predicting the outcome of matches. In particular, the key things to look at here are the percent concordant and the percent discordant. So what the 90.2% concordant is saying is that our model, this stepwise logistic regression model we came up with, correctly predicts the outcomes of 90.2% of the matches in the database. It only failed in 9.8%. So that is a whole lot better than a 50-50 random chance. So model does a very nice job of predicting the outcomes. And I guess if we go to the next slide.
Yeah, so I wanted to look at an example, and part of the inspiration for picking this project was I know there were some very controversial UFC decisions over the time. As you can see in the photo here, this was the Georgia St. Pierre versus Johnny Hendricks title match in 2013. And in the photo, you can see the face of the guy on the right. He's very upset with the judge's decision. And the guy on the left kind of looks super surprised. Mm-hmm. So this kind of came down to one of the worst judge decisions ever. And I wanted to test it in our model and kind of build a model to see if it could give a better result. A lot of the bias going into this fight was there was a lot of speculation that it was Georgia St. Pierre's last fight ever. And he was considered by many as the best UFC fighter ever. He had a lot of popularity, and they didn't want to see him go down with a loss in his last ever fight. And Johnny Hendricks at the time, he was 15-1 and was really good, but they knew he would be around a lot longer. So they kind of the UFC wanted to see Georgia St. Pierre win. And I think the judges definitely had a little bias when it came to that. So Georgia St. Pierre ended up winning the fight, but people for years have said that this was rigged and that it was one of the worst judges' decisions ever. So we're going to look at how our model compared to that. And here are the stats on the left from the fight. So of the 7 variables we included, this is looking at it in Johnny Hendricks' perspective. He destroyed him in control time on the ground, had way more seconds on the ground. He had more ground strikes. He also had more head strikes. They were exactly equal in knockdowns and reversals. And Georgia St. Pierre had more significant strikes and more takedowns. And then we kind of took that all and put it into the equation from the parameter estimates from our output that we got. And that was able to give us kind of a result, which Ryan's going to explain this part.
Yeah, so if we take a look at the equation here, this is the stepwise logistic regression that we came up with a few slides ago. And we plugged in the values for Johnny Hendricks into that equation, 9360 for difference in control time, 3 for difference in ground strikes, etc. And we crunched the numbers, and we came up with 1.2331. Now, again, not super straightforward to interpret that, since we're dealing with a logistic regression. So we have to exponentiate it. If we take the base of the natural logarithms e, raise it to the 1.2331 power, we get 3.43. So what this is saying is that in a situation where a fighter has these differences over their opponents, 9360 difference in control time, 3 difference in ground strikes, etc. When we have a situation like that, the fighter with these differences is generally going to be 3.43 times as likely to win the match as the other fighter. Yeah. So
basically, this leads to Hendricks, as he said, was 3.43 times more likely, and we can kind of conclude that the judges got this one wrong based on all those variables and kind of, if you take the names away and just look at the numbers and look at the total match instead of the individual rounds, Hendricks put on a better performance. His stats are better to predict a winner, and they indicated that he was more likely to win here. So some of the implications for this model is it can be used to measure controversial matches, as we just showed, especially when judges are being biased compared to their normal standards. So we looked at this as their normal standards, which was all the data we used before, but there are a few of the matches where there were some red flags where it seemed like they weren't being incredibly fair depending on how they were before. And it shows matches as a total result of who won more rounds. So that's what the data normally shows, is kind of who won more rounds. But as you know, in boxing or UFC, someone could completely dominate one round and then kind of just barely lose the other rounds. And in total, they could have way worse total fight stats, but it's not really factored in. And this kind of also weighs the impact of specific moves. So some of them had a lot higher significance in our model, like significant strikes and takedowns were really big. The takedown specifically, that doesn't happen much in a UFC fight. It might only happen 2-3 times, but when it does, it's impactful and it can really sway the decision of the judges, can completely change the outcome of the fight. So those were a lot higher than, say, each second that has someone in control on the ground. And this could definitely be useful for judges and fighters in preparation. The judges can kind of look at this and kind of be able to say, okay, if this person completely dominates in this area, this is how we should look at the match and score it. And also fighters can look at it in preparation, say they're going against someone who has fought similar fighters, has played similar competition, and they know that, yeah, you might not be able to beat this guy in head strikes, but you might be able to beat him in control time on the ground. So this is an area I'll look to attack. And if I can get to this bar here, then I can end up winning if it goes to judge decision. So there definitely are some areas of future research with this. One thing I wanted to do after this is kind of create a new scoring system based on just the results. So this was our logistic regression model was used to predict the results, but I kind of want to make my own scoring system that takes the similar parameter estimates and the weights of each move and is able to come up with a scoring system where you can just plug in the numbers into the equation and it should just kind of be able to tell you the winner. Our results use previous judges' decisions, so we can point out flaws in their scoring over time. So as I did with that one example, I pointed out the flaws in that and how that they definitely got the decision wrong there. But over time, like you can use this model to, if there's another controversial fight in the future, you can use it to point out the flaws in their scoring and say the refs got this one wrong. And also maybe sometimes in the judge's decision, certain things aren't factored in as much. So for example, the control time isn't factored into decision as much as maybe it should be. That could be something that the UFC looks at with their judges and say, hey, you need to look at this move more. It could be more impactful. Also, the UFC can use judges' scores as weighted results. So an idea that I was thinking of proposing, which coming from a statistics background, I think that this would make sense and kind of give a more fair outlook at everything, is 50% is the judge's decision, what they see, and then the other 50% of the decision is based on a computer model that figures out the results. So maybe if they used our model and then 3 judges, then that could be a better way to kind of choose the winner. Finally, the model can be used to predict future matches if the fighters had similar competition. So this is more so just to pick who's the winner after the fact, but you can kind of, if they're fighting the same people in the same weight class but they haven't matched up against each other yet, you can kind of plug both of their averages into the model to see who you think the winner would be. That's a little more flawed, but it's just another kind of thing you can do with this information. So here's our source. We got it from this Kaggle data set, and we'll now take any questions. And if you want to ask any more after the fact, here's both of our LinkedIns, and I have a YouTube channel where I was going to try and make a video on this in the future.
Thank you very much. Yeah, are there questions for Chris or Ryan? Well, then I've got maybe a sort of two-parter, I guess. Maybe answered this before, but like what percent of matches go to a judge's decision, and then is related to that, is playing for a win via judge's decision going to possibly lead you to a disadvantage in losing in some other way?
Yeah, I can answer that. So I don't have the exact number pulled up here. I remember looking at it before, but it's normally about a little less than half of the UFC matches go to a judge's decision. A lot are ended early. And so some fighters definitely try and get it to go to a decision, especially if they're good at wrestling, because they can kind of just get in position and hold the other person in control for the entire fight. That was kind of like the example we showed there. The one guy had like 9,000 seconds of control time that entire fight. So he kind of just wrestled him and stayed on top of him the entire fight. And that was how he thought he should have won, but the judges didn't look at it that way. So I think it definitely can be sometimes the fighters will decide to do that and try and get it to go to a judge's decision, but it's a risky game to play, especially if you're the underdog or you're going up against someone who's got a lot of popularity, because at the end of the day, it's the judge's decision who wins, and sometimes they end up picking someone just based off their name value, and that's what we hope to get eliminated from the sport, and that's what I want to see them use a computer model to pick the winners instead.
Thanks. And there's a question in chat, if you're able to see that and address that, related for waiting positions on the ground.
Yeah, that is something that I'd like to wait in the model, the different types on the ground. This one, this data set I had didn't have, I know you said, is there future hopes for waiting positions on the ground, half guard or side control? The data set I used didn't have a specific half guard or side control option. It just kind of had it as control as a time on the ground. So that's all they had. So if I can find a data set where it has the two different types, I think that would be really good, because that could explain more. Because of course there's a difference between if there's a half guard or side control, and sometimes it all depends. Sometimes you end up getting in a better position there, and it's more significant to have them in the side control than the half guard, because you can't get other strikes off on the ground. So I think that is something I want to look at. If they end up adding that into the data set, that could be something that makes the model look even better.
All right, well, thank you very much. I see that Russ just popped in. Do you want to take the logistics then?
Yeah, I was just gonna say I'm closing down the Zoom here for our 45-minute break. So everybody is expected to go outside and walk around and go get a little bit of physical activity, eat some lunch, and don't think about anything nerdy or sports related, even though I'm sitting here actually watching the OU football game. But yeah, I'm gonna close it down here in about 2 minutes entirely. So for y'all to come back, you'll need to re-click the Zoom link to come back in later. 12:45.
Thanks again, everyone.